Hello, Augies Worldwide. Today we're going to talk about common mode current. I'm Dave Casler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today's questions came quite recently from Michael Kenslow, KJ5MLK. And this is his question. He is doing this in regard to an Ask Dave column that I did earlier. He says, I still have a lot of study to do. I don't see how current in the inside of the coax shield is different than that on the outside of the coax shield. Well, the answer to your question is skin effect. Considering the connectors attached to the inside and outside of the shield, and that attaches to both surfaces of the connector, absolutely true. The wired woven shields are exposed to both the inside and outside of the shield surfaces throughout the length of the run. The foil wrap connects the inside to the outside all the length of the coax, and the process of soldering the shield to the connectors connects each strand of the shield completely submerged in the solder. I'm having a very difficult time visualizing the current voltage jumping to the next strand to keep it segregated on the inner or outer surface. Please point me to a resource that can help me get this digested. This is a piece of coax. It happens to be LMR 400. And let's look at the construction of it. Okay, we see right here, inside is an aluminum wire. You can see it's aluminum by looking right there. That is coated in copper. Okay, now why do we do that? Because at RF, or at very high voltages, the current tends to flow on the outside of the conductor. We call that the skin effect. Now you can prove that by going into Maxwell's equations directly, but that's a little over my head. So let's just take what the ARRL antenna book says and use the term skin effect. This foil, this is aluminum foil shield, gives it 100% coverage, and this right here is again part of the shield. Now we have to think again about skin effect. The current that is related to the current flowing through the center is carried on the inside of the shield. Using skin effect, that means it doesn't come through to the outside. Similarly, however, the outside of the shield can act almost like a third conductor if you're using RF, and you have a skin effect on the outside. And so it is possible to have this be at ground, this be at some other potential, which is the way it should be. But if there is a path for some of that current to come back down the outside of this, we call that common mode current. Now, common mode current is far easier to understand if we look at parallel wire line. Okay, as you see right here under the tape, each side here has a conductor. Okay, these are in parallel. This is called parallel wire line, and this happens to be often called window line because these windows are cut out. Sometimes we refer to this as open wire line. It's obviously not, it's not open. There is line that is open. The correct term for this is window line. Now, if we look at balanced line, this is a balanced feed line. We have current flowing this way and an equal and opposite going the other way. Now, this is RF current. You got to expand your thinking a little bit to this is the direction of the power flow in the system. Okay, so you've got a transmitter down here and you've got an antenna up here. A balanced antenna, or you've got a balun to convert it back. So operating properly, you have equal and opposite currents. Now that almost looks like DC, but you got to think, if this is the potential for here, then the potential on the other side for here is going to be the opposite of this, okay? So they're balanced. One side pushes, well, this side pulls, and then the other way around, okay? Now, what happens if there's something weird going up in the antenna, and there's a reflection or something that's amiss, something is amiss, and you get a common mode current? A common mode is what you might think. Instead of this is what you would call a differential mode, sometimes just called balanced. It is possible to have current, an additional current, flowing this way, equal and not opposite, equal to the equal current in each leg, okay? So instead of opposite each other, they're going the same direction. Since these have a direction in common, we call this common mode current, okay? And the problem with that is that if it's equal and opposite, or in other words, balanced, rather than unbalanced, okay? If it's balanced, the feed line is a feed line. If it's common mode or unbalanced, the feed line acts as an antenna, okay? So you don't want that. Now, how do we convert that to coax? How do we talk about common mode current in coax? We'll do that with this drawing right here. This is from the antenna book. I have version 23 as the antenna book. This is from chapter 24 that talks about transmission line system considerations. It's on page 2438, and it's figure 24.48, okay? And it talks about here skin effects, keeping them confined where they are in the line. This is important. This is how that works. Now, technically, you can explain this without reference to skin effects by going directly back to Maxwell's equations, but you're going to get the same answer. Maxwell's equations are graduate level mathematics. This is the coaxial feed line. We have the center conductor, which is this one right here, and we're going to put this out to 1/2 of the dipole. And now we've got the opposite. Remember, it comes on the outside of this. And the inside, the current flows on the inside wall. Again, this is RF current. It looks like it's direct current, but it's not. It's RFAC. It's in the direction of the current at the moment. Here comes the current up the inside to go out over here. Now, the problem is, as you pointed out, the inside and the outside meet right there, okay? So some of that current can, and does often, this is the problem with feeding a dipole directly rather than with a balun. Some of that current comes right down the other side over here. So it's going this way inside and that way going outside. Now notice where this current goes. It goes hopefully to ground. Normally, you want to have the coax shield at ground, and you do for DC. But if you don't have a balun up here, think of a balun as a transformer, okay? So you've got unbalanced here and balanced here, okay? And this will be ground. But if you do it like this, it's very easy to get current on the outside of this. And for coaxial, we call this common mode. Okay, because this current flows down all the way around, but does not involve the center conductor. This is called common mode current. Hopefully, you will connect it directly to ground at some point so you can ground it out. If you do not ground it, it'll go right into the source, the transmitter. The problem with this is that you now have RF current coming into the station, which can make the chassis hot, the microphone hot, and yes, I've been shocked by this at points. Of course, I go out and fix the problem. Now, this way of making dipoles is extremely common, and I do it too, just routinely. Ideally, you should have a balun here, which will keep this from happening. Okay, if it becomes a problem, that's the fix. You put a balun here. Or you can put ferrite beads around this, a bunch of ferrite beads around here. And this poses a high impedance to the common mode current. And so the common mode current won't flow through it because it sees that as a high value resistor. And so it stops. Of course, if it stops here, it doesn't go there, but you put these up near the feed point. The other thing you can do is what's called a coax balun, and just take some coax and wrap it in a circle, 9 or 10 loops, 9 inches to a foot in diameter. Bring it down here and connect these together with tape or whatever your favorite adhesive is. Now, what happens here is the outside of the coax is seeing an inductance, and the reactance at the frequency we're looking at is high enough that this appears to be a high resistance to the common mode currents. That's another way of getting rid of it. And as I mentioned, the third way to get rid of it is a balun. Now, a balun we think of as a transformer, but actually the term balun refers to the function of what we're using here. So that's a balun, this is a balun, and a transformer is a balun, because they provide the balun function of converting balanced line to unbalanced so it can work with coax. Okay? Now, if you've got the ferrite beads, that's often less expensive. You put quite a few of them on there. I think on my MFJ hex beam there's like 20 of them. Here, this requires about 25 feet of coax at $1.50 a foot. You can see that that's going to cost you some money too. Now, a simple balun you can get from DX Engineering, a balun from LDG that's at 1:1. So 50 ohms here, 50 ohms here, and it's about $30. Okay, so I hope that answers your question. The key to this is that RF energy behaves very differently from DC energy. If you had low voltage DC like 12 volts going over your coax like to a remote antenna tuner to power it, then that DC will behave like it normally would. It uses all of the conductor, okay? So you can use that to power DC type things. RF does not behave like DC. Our normal Ohm's law kind of thing, where the voltage is equal to the current times the resistance, works at DC. But when you get into RF, things start to behave funny, okay? Like the skin effect. Inside the coax, what's inside the coax stays inside the coax. Ideally, you want the outer shield grounded, and you don't want any common mode current coming back the outside. You can get rid of the common mode current by, like at the antenna, you can connect the coax to ground through a barrel connector or something like that, and then tying that off to the ground or the tower lag or whatever your mast is, so that that will stop any common mode currents from going further. Ideally, you want to stop the common mode currents at the source, which is usually the antenna. So a balun, the ferrite beads, or a choke balun can do the job. All this is addressed in the antenna handbook in more detail than it would be in the regular radio amateur's handbook. They update the ARRL antenna book every few years, whereas the amateur radio handbook is updated every year. Okay, so I hope that helps. Just think, you're talking about two entirely different phenomena. Electricity at DC, which uses the basic form of Ohm's law, or electricity at RF, which obeys Maxwell's equations, and Z, the impedance, equaling the current times the voltage times the cosine of the phase angle, the difference in between, is a special case of the Maxwell's equations. But what we're doing here is just thinking, okay, RF does funny things. It flows right on the surface of whatever conductor. Like, for example, that's why LMR 400 can use an aluminum in the inside and then copper plate it, because most of the current will flow through the copper. Now you say, wait a minute, copper and aluminum are dissimilar metals. That is absolutely true. Where you would get a problem between them is if the aluminum and copper are exposed to water, which will cause corrosion. Okay, so otherwise we keep them apart. So there you have it. I hope that helps. And until we next meet, 73.